Good. You got enough ahead of the game that you're probably handling that tough curriculum you're encountering. That truly is the secret of math, is to stay ahead of it, and hopefully we'll get you to that spot in calculus.
Yes, sir.
So I've kind of covered what I think is the most important stuff in differential calculus, but not really. There's a few more things that we need to talk about that I've kind of semi-covered, but not as much as I perhaps should have.
All right.
Let's talk about some of these theorems that you encounter in calculus. They're not so much theorems where you have a lot of problems that you can do. They're kind of the theorems that are used to justify more complicated theorems. In other words, they're used as the reason in a proof.
Okay.
Okay. We talked about one of them last time, which is the extreme value theorem.
Yes, sir.
Which merely says that if you have a closed interval and the thing is continuous, then there will be a minimum and a maximum on that interval.
Yes, sir.
Which might stand to reason and is quite logical, but nonetheless, that's a theorem. That's the one thing about math is you have to prove everything. If something's equal to itself, you have to prove it. It's the reflexive property. So we've talked a little bit about relative extrema, right? In other words,
yes, sir.
Here, let me open up my writing tool here. If you have a graph that looks like this, you know that the critical, there's a term called critical number. And
Yes,
so far, the only thing we've talked about is places where the first derivative is equal to 0, which would be that place and that place. Okay? So those would be critical numbers here. If we're attempting to find a local maximum or a local minimum, it's going to be where the first derivative is 0, because the slope of the tangent line is flat, both of those forms. Well, that's all good, but sometimes we have something like this. And we don't have a first derivative that's equal to 0.
Okay, I see.
That function is absolute value of x. And the way you can look at it is as a piecewise function. It's equal to x whenever x is greater than 0, and it's equal to negative x whenever x is less than 0.
Yes, sir.
And it's equal to x at 0. So I suppose I can do this or that, and that. Okay? But if we had this as a function and we were trying to find the minimum on it, well, taking the first derivative isn't going to do us any good.
That's right.
Because the first derivative is not defined at that cusp.
Okay.
So the definition of critical number is where first derivative is equal to 0 or undefined.
Okay, so the critical number
is
where?
Right. In other words, it's A critical number is going to be equal to either 0, all critical or all first derivatives that are equal to 0, those are critical numbers, and all first derivatives that don't exist.
Okay.
That's a critical number. And maybe even your endpoints.
Okay.
And I say that even though I'm reading my book and I can't figure out whether that is the precise definition of critical number. But if you're looking for absolute maximums and absolute minimums, then you always need to consider your endpoints. Even on this function right there, if I had endpoints like that and it was a closed interval, then those would be absolute maximums. And they would be on the endpoint. So critical numbers are really three things, let's call them.
All right.
First derivatives equal to 0, first derivatives that are undefined, or endpoints. And that's critical because you so frequently have functions where you're trying to calculate relative minimum, relative maximums, or absolute minimums, absolute maximums. And you need to consider all critical numbers. All points on the x-axis that are critical.
Okay.
Now let's examine this function just a little bit. I guess I need to mention this because I didn't mention it the first go around. There's another definition for first derivative.
All right.
First derivative equals the regular definition is this. Remember that one?
Okay.
That's the one I like the most. That is the most robust, meaning it handles every single function, and then you can substitute the point that you're interested in to find out what the slope of the tangent line is at an x value of that. Okay, so to me, this is the best one by a lot. But there is another one. Yeah, you're almost certainly going to get this.
All right.
Which is f of x minus f of a all over x minus a as x goes to a, not c. Notice that this is quite similar. What this is the definition of first derivative at a single point, a. So this is a much tighter, less useful definition because it only applies at a single point, a, on the x-axis. So if you have an a right there, and I want to know what the slope of the tangent line is, then I can use this formula. Now, like I said, I don't much care to teach this first go around because if you want to find out what the slope is at a particular point, you can use the original definition, come up with the function that is the slope, and substitute the point. However, this definition has one very useful spot where it's very helpful, and that is around cusps or corners.
Okay.
Okay.
I see. Because it's for a specific point.
Right. So if I want to figure out what the slope of the tangent line is at x equals 0, I'm going to use this definition. So I'm going to take the limit of
Okay.
Okay, you with me?
Yes, sir.
Okay. And that equals f of x is the absolute value of x, minus f of 0 is 0, and that's just x. So if I calculate it as a two-way limit, in other words, if I figure out what the limit is as I approach 0 from the left, it's -1.
Okay.
If I figure out what the limit is as I approach 0 from the right, it's +1. Since the limit from the left is different than the limit from the right, it means it's not differentiable at that point. And this is the only way I can really mathematically prove it to you.
Okay.
In other words, if I use the more robust formula, f of x plus h, it doesn't tell you much about what's going on at this point. But if I use this specific definition of first derivative, it does. You just have to examine it from the left and from the right. If the slope does not come out to be the same, then it's a corner or a cusp. So there is a mathematical definition of a corner or a cusp. And it doesn't really matter. You know, you can have all kinds of corners and cusps. You can have something like this. That's going to be a corner. But how can you tell mathematically? It's by examining the first derivative from both sides of that point on the x-axis.
Okay.
From the left and from the right.
And it's not differentiable because
the slope from the left is not the same as the slope from the right. That's has to be the same. It's kind of like, remember when we were doing limits and we had, if the limit from the left is not the same as the limit from the right, then the limit doesn't exist.
that's right.
Same thing with derivative. If you look at it as it approaches a from the right, and it's not the same as it when it approaches a from the left, that derivative does not exist.
Yes, sir.
Okay? Let's look at this situation. The function that is represented by that graph is that. So if I asked you, where is the word relative maximum or absolute maximum appropriate?
Relative?
Both, actually. Come on.
Both. Okay.
In other words, it's definitely relative, and usually we're looking for relative in most calculus problems. I can't remember too many problems where you're looking for absolute maximums or absolute minimums. It's almost always relative because usually you have constraints on your domain. The domain is not usually all real numbers. Okay, it's kind of like, remember that problem about the box where you start with a flat rectangular piece of cardboard and you cut out little corners, fold it up into a box.
Yes, sir.
The domain of the x values there was limited by the dimensions of the flat piece of cardboard.
That's right.
So we were dealing with a fairly narrow range of possible x values. Well, most problems are like that. Okay, so it's almost always the relative minimum or maximum that you're trying to find. And if I wanted to know what that point was, how am I going to do it?
You would find the first derivative of it.
Okay, let's do that just for practice.
All right.
Now, hold on. Let me write this and start it right there. So f prime of x is going to be what?
Okay, so that is...
And tell me how you're going to do it, because I might be able to suggest an easier way. Tell me which rule you're going to use.
This is the... What's the rule that does the inside-outside?
That's the chain rule.
The chain rule.
Definitely going to be involved in taking this derivative. What else?
The
You got four rules in differential calculus. You got the power rule, you got the product rule, you got the quotient rule, and you got the chain rule.
and chain. All right. So we're going to be using the product as well. Is that right?
And what else?
As well as the quotient.
Okay. And you already mentioned the chain, but actually we won't need to use the chain if we use the product. And in fact, let's do a little bit of arithmetic here, and I think you can see, well, you will see, that there's a much easier way to differentiate that. The quotient rule, if you'll remember, is quite complicated.
That's right.
Top times or it's the bottom times the derivative of the top minus the reverse all over the bottom square. That thing's going to blow up on you. So if we look at that function and see, well, what if we simplify it a little bit? Well, it's definitely this. Right?
Yes, sir.
That definitely is this. And that is this. Let me rewrite it even further because I'm out of room here. I'll skip a step and write that as 9x to the minus 1 minus 27x to the minus 3. Okay?
All right.
Now take the first derivative. It's much easier. Because we simplified the function, we turned it into there's only one rule to use. What is it?
It is the chain rule.
No, it's the power rule.
Oh, wait. Power rule.
Power rule is where you start with that exponent.
That's right.
And you subtract 1 from it after you finish multiplying the coefficient by that exponent. So what do we got here?
All right. So we're going to have negative 9 x to the minus 2 plus 81 x to the minus 4.
Notice how much simpler that was.
Yes.
We'd still be reducing the quotient. If we'd have used the quotient rule on this, we'd still be simplifying it, and the algebra would be really complicated. So don't overlook doing these kind of simplifications. They're extremely important. Okay. Now what?
All right. So now we have to.
Here, I'll rewrite it back into this format.
Oh.
But what's the fundamental thing you're doing when you're looking for a relative maximum?
You're trying to find its tangent line.
It's horizontal tangent.
Is it equal to 0?
Exactly. Well, we're looking at the derivative function, so we're going to set that equal to 0.
Yes.
And solve for it.
All right.
Now, solving for it, if I multiply both sides by x to the 4th, oops, correct?
That's right.
And then I get minus x squared equals minus 9. Get rid of the minus signs. What's my answer?
Positive or negative 3.
Now look at the graph. What's my answer?
Positive 3.
Exactly. In other words, it's true that x squared equals 9 and that x would equal plus or minus 3. I'm glad you remembered that because most people forget that. But sometimes both answers aren't correct. Only one is.
That's right.
The other answer is more or less extraneous. And you can certainly see that there's one aspect of this original function. X cannot be 0. Because that would mean we're dividing by 0. The original function had x cubed in the denominator.
That's right.
So this red line approaches x equals 0, but certainly never goes on the other side of it. So the minus 3 is out on this. Only the plus 3. And if we wanted to know what the y value was when x is equal to plus 3, we just plug plus 3 in, not to the first derivative function. It served our purpose already. It told us where we had a horizontal tangent line.
That's right.
But if we plug in x equals 3 into the original function, we'll get the y value. And
that's right.
that y value ends up being, just so I can save myself a little bit of arithmetic, 3, 2 is, in other words, that point is 2. That point right there is 3, 2.
Yes, sir.
Okay. Might be useful to review this one.
Okay.
I think I did this once for you, but it's actually pretty helpful. In understanding what the first derivative, what's the top function?
That is the sine of x. Bottom is the cosine.
And what do we know about the derivative of sine? What is it?
It is derivative. The derivative of the sine, like overall, or at a specific?
Yeah, no, the derivative of that function. Sine is a function. Okay, so its derivative is the cosine. Now let's examine why that's true.
That's right. Okay.
Well, what's the slope of, if we look at the sine function only, what's the slope of the tangent line at 0?
That is.
What's that slope?
Oh, yeah, that's 1.
Exactly. That's this point right there. Now, if we look at the slope of the tangent line at pi over 2, what's that?
That is 0. It's
that point right there. If we look at the slope of the tangent line at pi, what is it?
It is -1.
That's that point right there. And if we look at the slope of the tangent line at 3 pi over 2, what is it?
0.
Which is that point right there. So you can see why the first derivative of sine is cosine. At every single point, the cosine will tell you what the slope of the tangent line is on the sine, including if you go backwards. In other words, this is with all real numbers being the domain, going backwards on both of them. In other words, I always only am drawing one period of these curves. It's important to understand that they actually go from negative infinity to positive infinity.
That's right.
Okay. I guess that's all I need to say about that. All right, back to the definition of critical number. It's not the endpoints. It's between the endpoints wherever the first derivative is 0 or undefined. It's those two things only.
So it's not the endpoints.
No.
It's what?
It's where the first derivative is equal to 0 or undefined.
Okay.
All right?
So it is only two things.
Yes, it's only two things. Now, an example of undefined would be something like this. If my first derivative came out to be this, where am I undefined?
If x is equal to 0.
Okay, so that's a critical point.
Okay.
Or rather, a critical number. Critical numbers always refer to the x values.
Okay.
And there's another 0 point there's another critical. First of all, if I set this first derivative equal to 0 to see if there's any points where the first derivative is equal to 0, which is another critical number, how do I solve that equation?
All right.
Whenever, kind of memorize this. You could do this a couple of ways, but I can save you some help, or I can provide some help. Whenever a rational function is equal to 0,
Okay.
its numerator is equal to 0. Always.
That's right. That's right.
And the way you would discover that is if you multiply both sides by x squared, you would get 3x minus 2 equals 0. So another value where the first derivative is equal to 0 is at x equals 2/3.
Okay.
So this particular function has two critical numbers. What are they?
It is 0 and 2/3.
That's it.
And that's because when it's 0, it's undefined, and when it's 2/3, it's 0.
Exactly. Well put. Let's talk about Raleigh's theorem.
All right.
Interesting because Raleigh was a 17th century mathematician, one of the best, who went to his grave not believing in calculus. Well, actually what I'm reading here says later in life he did come to see the usefulness of calculus, but he was always suspect about it because this whole thing of dividing by zero is so anti-mathematical. You know, everybody's top 10 list of things you can't do in math is divide by zero.
That's right.
All of the top mathematicians had difficulty accepting. Even Newton, who invented calculus, did not include it in his most famous math publication of all time, which to this day still is the most important or famous math publication of all time, which was Principia Mathematica.
Wow.
And he published that in 1665.
Wow.
Did not include any calculus in it.
Huh.
Yet he had actually discovered calculus 20 years earlier. He didn't put it in that book because he didn't even trust it 100%.
Because of dividing by zero?
Yeah. That
Wow.
you can't believe what a new concept that would have been. When for thousands of years, you could not divide by zero. That was where you started all mathematics at. And then he comes along and starts talking about it's not really division by zero. It's division by a differential that approaches zero. The definition of a differential is an extremely small number that approaches, that's going to go to zero. Okay, so he kind of gets around the rules by the limits, and it turns out to be completely legit. Calculus ends up being the most useful mathematics that's ever been discovered in terms of applications, to the real world. So not only was calculus real, but extremely useful. Now, what Raleigh's theorem says is that if f is continuous on a closed interval and differentiable on the open interval, then there is at least one number in the interval such that f prime of c equals 0. Let me show you a couple examples.
Okay.
Notice we have a function on a closed interval that is continuous and differentiable. No matter what point I want to select on the x-axis in that interval, I can find the slope of the tangent line, right? There's no corners or cusps or missing spots. So it's continuous and differentiable on that interval. And what Raleigh's theorem says is that if that's the case, then there has to be one point in that interval, at least one, where the first derivative is equal to 0.
Yes, sir.
And obviously here, it's right there.
At the local and absolute maximum.
Yeah. However, there's something extremely wrong with this. And that is, what if you have a function like this? and I'm dealing on that interval to there, well, there's no place on that function where the first derivative is equal to 0. Okay. The actual Raleigh's theorem, I misstated it.
All right.
Additional part to it. In other words, on the closed interval a to b,
Okay.
if there is a single point where f of a is equal to f of b, then Raleigh's theorem says there has to be a point in between. Notice that in this particular instance, that is both f of a and f of b.
Yes, sir.
So as long as there is an a and a b in that interval such that f of a is equal to f of b, then it says there has to be some point c where the first derivative evaluated at c is equal to 0. That's what Raleigh's theorem says. And notice that in the case that I was talking about, there is no point in that interval where f of a equals f of b. So Raleigh's theorem does not apply because that is not true for that bottom function.
Okay, I see.
There are no a and b where f of a is equal to f of b. So Raleigh's theorem applies very precisely to the case where f of a equals f of b. Another function that it also would apply in is something like this. In other words, it does not have to be differentiable on the interval, which I originally said it did. It just has to be continuous.
Okay.
If it's continuous on the interval, and there is a point where f of a equals f of b, like right here, because that, once again, is both f of a and also f of b, right? So we have a point, a and b, where f of a equals f of b, and what Raleigh's theorem says is there has to be, hold on a second. Well, I take it back. It does have to be differentiable. Okay, we're honing in on Raleigh's theorem. I apologize. But Raleigh's theorem says it has to be continuous and it has to be differentiable. In other words, what Raleigh's theorem would normally say is there has to be a point C where the derivative is equal to 0. Well, you can see from this function here, there is no such point. Not there. That is not C. The derivative there doesn't exist.
That's right.
There's no other point on that function where the slope of the tangent line is equal to 0. So Raleigh's theorem does not apply because it's not differentiable over the interval from A to B.
Yes, sir.
Okay. But no matter what kind of function you can draw, I could draw a function like this, not meant to be smooth, and there's a closed interval, and the function, I don't know what it is, but that's supposed to be smooth. I know that there's a point A and B such that f of A is equal to f of B. And the function is continuous, and the function is differentiable at all points. Everything is smooth. There's no cusps or corners. It satisfies the three things that have to be satisfied. And what this says is there has to be at least one point. Okay?
Where the first derivative is 0.
Yeah, and we can see, in fact, that there are numerous points here. There's that point. There's this point. There's this point. There's that point. There's that point. So all Raleigh's theorem says is there has to be at least one point where the first derivative is flat, horizontal. Okay. Mean value theorem. That's probably one that comes up more often in calculus. There's three of them. There's Raleigh's theorem, there's the mean value theorem, and there's the intermediate value theorem. Conceptually, let's talk about the mean value theorem.
All right.
The mean value theorem says whatever, if you have a continuous function on a closed interval and it's differentiable on the open interval, same thing as Raleigh's theorem. It has to be differentiable on the open interval. What the mean value theorem says is basically, if I take the average slope between points A and B,
okay,
that is going to be f of B minus f of A, all divided by B minus A. That's the slope between that point and that point, as defined by rise over run. The rise, that's f of A, that's f of B. So f of B minus f of A is the rise, and the run is B minus A, right?
okay,
So the average slope between A and B, what the mean value theorem says is there has to be a point somewhere in between A and B where the slope of the tangent line equals that average slope.
okay,
In other words, there's going to be some point where that thing is equal to f of C. F prime of C.
all right,
In this case, there's the slope of that. And what the mean value theorem says is there has to be some point on this thing where there is another slope of the tangent line that matches that average.
okay.
So basic formula would be f.
So instead of the first derivative being 0, it's the first derivative is equal to the slope.
This right here.
Okay.
In other words, the way, and there are some problems here we can do on this one that will clarify this a little bit more. But basically it says whatever the average slope is from point A to point B, there has to be some place in between where the first derivative has that same slope.
Yes,
And that's what this statement right there says. Because f of B minus f of A over B minus A is the slope between A and B. And this says there's a first derivative at some point C that matches that.
Yes, sir.
So let's do it on a problem. Let's apply this. And here's the function. Find all values of C in the interval from the open interval from 1 to 4, such that
Okay.
f prime of C equals f of B minus f of A all over B minus A. Okay?
All right.
So, what's the first thing we need to do?
All right, so we need to plug in B and A to f of x.
Okay? So,
All right, so
f of
f of B
4 minus f of 1 all over 4 minus 1. So what is f of 4?
it's 1.
No. Plug in
Oh, wait.
4 for x.
It's 4. It's 4.
And what is f of 1?
F of 1 is 1.
So this entity on the right over here, the lower right, is 3 over 3.
Yes, sir.
So the average slope between point 1 and point 4 is 1.
Yes, sir.
Right? So
That's right.
we want to find where the first derivative of this function is equal to 1. Not 0, but 1.
Yes, sir.
So let's take the first derivative of that function.
All right. So we're going to have 5 minus 4 times x to the negative 1. To make it simple. So that's 5 minus...
What's the first derivative? Start with the first term.
That is 0, so it's
Correct.
just...
So that term goes away. The 5 goes away.
And then we have positive 4 x to the negative 2. And we can set that...
Normally we're setting that equal to 0 when we're looking for relative minimums and maximums. But in this case, we're going to set it to what we know to be the average slope between A and B, which is 1.
Yes, sir.
Solve that.
All right. Positive or negative 2.
Right. And with this function, there is both a positive and a negative. In fact, this function is hyperbolic. So it's going to look something like that. And, interesting. That thing's not differentiable. Oh, it is differentiable between 1 and 4. Yeah. So on the interval 1 to 4, what's the answer?
That would be 2.
Yeah, just the plus. So because we're only talking about the interval from 1 to 4, it takes away the minus answer. You can kind of see where that minus answer came from. Yeah, I've drawn this thing incorrectly. If I were to draw it correctly, I would have a point between 1 and 4 where the slope is equal to 1. Yeah, I guess it's more like this. Yeah, that's the way these hyperbolic functions graph when they're negative. Okay, in other words, I have a minus 4 over x. And at x equal 2, we do have a slope of the tangent line that is positive 1. And you'll notice that at x equal minus 2, we also have a slope of the tangent line that is positive 1. So in a sense, plus and minus 2 was correct, but because we're only looking at the interval from 1 to 4, it eliminates this hyperbola on the left side of the y-axis.
That's right.
So it's only really talking about that one. But that's the way the mean value theorem works. It's kind of the same as saying you're looking for relative minimum and maximum by setting the first derivative equal to 0, but instead of 0, you're setting it equal to a number that represents the average change in that function, the original function, when I go from 1 to 4. What's the average change in the function when I go from that point to that point? Use this f of b minus f of a all over b minus a.
Yes, sir.
All right. I hope I didn't make that too complicated. It took me a long time to understand that.
Yes.
But anyway, that is the mean value theorem. All right. Talk about another important aspect of differential calculus, and that is what happens to the first derivative of a function when here I have a page here that's perfect for talking about this. Find it and bring it up on the screen. I think it's this one right here. Sorry. Gosh, I'm going to have to open these to see if I got the right one. See what happens if I double click on it, whether I'm looking at the right one. Ah. I forgot what the name of this graph was, but sorry. It'd have been a lot quicker if I'd opened it with paint. This is terrible, terribly slow. I'll remember next time to never double click on these. Well, it's got to be this by default. Yeah. So what we're looking at here is a function, the original curve on top. The curve below that is the first derivative. And the curve below that is the second derivative.
Okay.
Okay. And hold on one second. an
I see.
aspect to these things that we haven't really talked about much. And that is when a function is increasing, its first derivative is always positive. If we look at this function, the top function, you can see that it's increasing from that point to that point, right?
Yes, sir.
Look what its first derivative is. It's positive.
Yes, sir.
Its first derivative is decreasing, but it's still above the x-axis between those 2 points. In other words, this whole area right there, the first derivative is positive.
Yes, sir.
You with me? When the first derivative gets to its relative maximum, or excuse me, when the function reaches its relative maximum at that point right there, the first derivative is 0. And then from this point to this point, the function starts decreasing.
Yes, sir.
Well, whenever the function is decreasing, the first derivative is always negative. And if you look at the first derivative between that point and that point, it's negative.
Okay.
Again, when we find a point where the slope is 0, the first derivative better be 0, and it is right there. And then the original function starts increasing again. Forever, actually. And its first derivative is always positive. Whenever the original function is increasing, the first derivative is positive. When it's decreasing, the first derivative is negative.
Okay.
And if you look at the second derivative, the same rules apply. In other words, let's look at the second derivative. Remember, the second derivative is merely the first derivative of the first derivative. Well, if we look at the first derivative, it's decreasing from there to there, right?
Yes, sir.
Well, that whole time, the second derivative is negative from there to there. It's in negative territory. And it's extremely easy to get confused when you're talking about negative versus increasing or decreasing. They're different. The first derivative, if you treat this as its own function completely, which you can do, then this function down here is merely the first derivative of the function that's above it. And it has to follow those same rules. Well, if we look at that derivative function, it only has 2 things. It's decreasing to there, and then it's increasing after that. So the derivative of that function has to be positive, or excuse me, negative all the way up to there, and then it's positive all the way after.
Yes, sir.
So this should solidify to you about increasing and decreasing of functions, what they mean for the slope. If you think about it, whenever a function is decreasing, it has a negative slope, right? And that's what first derivative is the slope.
Yes, sir.
So whenever something has nothing but negative slopes, the first derivative is going to be negative during that whole time. And if you want to know how, I mean, if I draw a more complicated function like that, well, it's increasing, hold on a second here. It's increasing from there to there, right?
Yes, sir.
So the first derivative's got to be positive between those 2 points. Nothing but positive.
Yes, sir.
And it's 0 at that point, the first derivative is. But then the first derivative between that point and the x, it's decreasing the original function. So the first derivative would be negative between those 2 points. Then it goes back to increasing between the x's. So the first derivative is going to be positive. Then it goes to decreasing. So the first derivative is going to be negative. And then it goes back to gradually increasing. So the first derivative would be positive. So I could actually construct a semi-first derivative curve without doing the math In other words, without knowing what that function is, just looking at it, I can see, well, gee, the slope of the tangent line right there is 1, approximately. So that point is on my derivative curve. And then from there to there, I know my first derivative is positive. All of those slopes are positive. And it looks like it stays pretty close to 1. So the first derivative might look something like that. And then I can see that at that point, it's got to be at 0. So really the first derivative is doing something like this. With me?
Yes, sir.
So what this principle does is allows us to approximate the first derivative based just on the graph, on looking at it.
Wow.
Whereas, like I said, I have no idea what the function is that I just randomly drew. I can still draw the first derivative curve of it, or at least something that is approximately correct.
Yes, sir.
Okay? And vice versa. Where differential calculus starts getting a little difficult is when they give you the first derivative curve and they ask you come up with the original function curve. So you kind of have to work backwards in your thinking. But very doable.
Yes, sir.
And the same thing is actually there's a point in differential calculus where they'll give you the derivative function and they want you to come up with the original function, based strictly on the logic of increasing functions are positive first derivative, decreasing functions are negative first derivative. So if they give you a first derivative curve, you can kind of work backwards to figure out what the original function curve looks like. And the reason that's valuable is because you don't always know what these functions are. They don't always give you the function as a polynomial or a rational function. They'll just give you the curve of the derivative. Go from there. Figure out what the curve of the function looks like. So
Yes,
we'll do that for a little bit, is work on problems like that for the next session or two. And I've gone over your time, so I'll let you go here. But certainly feel free, if you have any questions about the stuff you're doing in class, feel free to bring that up. I mentioned once again, if you have any questions at all about it. Because you're taking an honors type class, aren't you? Or is it just a college class?
Yes, sir. It's AP.
It's AP. Okay. So
Well, math is, yes, sir. Math is on.
you're bound to have some level of difficulties in that class that we may not have covered in all the work we put in prior to this summer. I mean, we did a lot of, you took me to my limits on some of these pre-calc subjects. You did. You went to harder difficulties than any other students I've had. So it may be that you've already covered the most difficult things you will get in the AP class. I don't know, but certainly feel free to bring some up if you don't have complete understanding of them.
Yes, sir.
All right.
All right.
Garrison, I will let you go. Have a good day.
Yes, sir. You too.
Talk to you next week.
All right. See you then.
Bye-bye.